This is section 6.2 on anti-differentiation by substitution. In example 1, they introduce the term indefinite integral. To evaluate this indefinite integral, meaning we don't have any indices or indexes here, of x squared minus sine x, it's simply 1/3 x to the third plus cosine x plus c. So this is an indefinite integral. We're not integrating over two different values. It's just simply the antiderivative. In example 3, we want to pay attention to the differential. In other words, these are the differentials, dx, du, and dx. In this case, we let f of x equal x to the third plus 1 and let u equal x squared. We want to find each of the following antiderivatives in terms of the variable x. So all the answers will end up having x's. None of them will end in any sort of u. In letter A, we substitute x to the third plus 1 in for f of x, and we are differentiating with respect to the variable x. So this one is pretty straightforward. The answer is 1/4 x to the fourth plus x plus c, and this is already in terms of the variable x. Letter B, we want f of u, which means instead of having x's in f of x, we're going to plug u's in for the x's. So we end up having u to the third plus 1 du. So we're going to integrate with respect to u, not x. When we do that, we get 1/4 u to the fourth plus u, and then plus c, of course. But we can't end it in u because the instructions say in terms of x. So u equals x squared, so we'll replace the u's with x squared. We end up with 1/4 x to the eighth plus x squared, and then plus c. In the last one, we have f of u, so we will replace the x in the function with u's. But since we are differentiating with respect to x, instead of writing u's here, we'll put x squared in right away because we have to differentiate with respect to the variable x and not u as in letter B. So this becomes x to the sixth. So the antiderivative will be 1/7 x to the seventh. The antiderivative of 1 is x, and we have plus c. In example 4, we finally get to integration using substitution. Here's our first example. The integral of sine of x e to the cosine x dx. Well, it's not really apparent what the antiderivative of this will be. So we're going to let u equal the top, which is the cosine of x. That way, du equals negative sine of x. So the derivative of each of these, each side of this equation, well, the left side is just du, or 1. And the right side, the derivative of cosine x is negative sine x dx. Well, now we're going to make the substitution. Where we see the cosine, we're going to put u. And where we see sine of x dx, we're actually going to put negative du, because I could divide both sides by negative. So negative du. Sine of x dx is replaced with negative du. The antiderivative of e to the u is e to the u, but there's a negative that goes along with e to the u. And we didn't start out with u's in the original equation, so we can't end with u's. So the final answer is minus e cosine x. And I have forgotten plus c. Shame on me. Anyway, there's the plus c. In example 5, we're also going to use substitution. In this case, it's not, I don't think it's all that apparent what the antiderivative of this would be. But we can, I think, very easily do the antiderivative if you use this u substitution. We're going to let u equal 5 plus 2x to the third. The derivative of each side, well, first of all, the derivative of u would be 1, and the derivative of the right side would be 6x squared, and then dx. We don't have a 1/6 in this original function, so, well, excuse me, we don't have a 6 in here, so, but we do have an x squared. So if we divide by 6, I can replace x squared dx with 1/6 the du. Using substitution, we can replace 5 plus 2x to the third with u, and we can replace x squared dx with 1/6 du, and I've put the 1/6 out in front already. The antiderivative of u to the 1/2, let me write that so you can visualize that we're really taking the antiderivative of u to the 1/2. If we add 2/2 to 1/2, in other words, adding 1 to the power, we get 3/2. And when we would do the power rule, the 2/3 and 3/2 would cancel, leaving a 1 out front. And then plus c. 1/6 times 2/3 is 1/9, and then we didn't start with u, so we aren't able to end with u, so making the replacement back in for u is 5 plus 2x to the third to the 3/2 plus c, and there's our final answer. That's the antiderivative of the original function. In example 6, well, we don't know what we take the derivative of to get cotangent. We certainly know what the derivative of cotangent is, but that's not the direction we're going. We're going backwards with this. Well, we employ a little trick here. We can turn cotangent into cosine over sine. If we let u equal the sine of 7x, the derivative is 7 cosine of 7x. We have the sine of 7x here in the bottom, so we can make that replacement. But we don't have a 7 cosine 7x dx. We have a cosine 7x dx. So we're kind of missing the 7 to make a direct replacement. But we can fix that by dividing by 7. So we'll have 1/7 du equals the cosine of 7x dx. So now we do have the cosine of 7x dx, and we can replace that with 1/7 du. So here's the substitution. Sine of 7x is replaced by u. And then the cosine 7x dx is replaced by 1/7 du. And I've already pulled the 1/7 out front. The antiderivative of 1 over u is a natural log of u. Now we have to have absolute value here because we cannot take the natural log of negative values. And if we had a definite integral and either of these were negative, then we'd have a problem on our hands. But if we put absolute value in with it, then there's no chance of ever taking the natural log of a negative number. We have plus c, of course. Well, we didn't start with u, we can't end with u. U is sine of 7x, so we make that replacement. And in the end, here is your answer for the indefinite integral of example 6. In example 7, we're going to set up a substitution with a trigonometric identity. So we're going to take a, b, and c and change the way they look in order for us to be able to use u substitution. Letter A, 1 over cosine squared is secant squared of 2x. There's a very simple u substitution for this one. The u would be 2x, so du would be 2 dx. Divide by 2, and the substitution is the 2x is replaced by the u, and the dx is replaced by 1/2 du. Antiderivative is 1/2 tangent of u plus c, and then we replace the u with 2x. In letter B, cotangent of 3x can be replaced with cosecant squared of 3x minus 1 by the Pythagorean identities that you learned in trigonometry. In this case, we let u equal 3x, so the du is 3 dx. It's implicit differentiation of both sides. We don't have a 3 dx, but we have a 1 dx, and I don't mean this one. It's separate from the one that would be in front of the dx here. So we divide by 3. The replacement is the 3x becomes u. The antiderivative of cosecant would be negative cotangent. Antiderivative of 1 would be u. And the 1/3 kind of comes along with. Distributing the 1/3 gives us negative 1/3 cotangent of 3x minus x, and then plus c. And finally, in the last one, we can replace cosine to the 3rd x with cosine squared times cosine x dx. By Pythagorean identity, we have 1 minus sine squared x cosine x. We will just make the u substitution with sine x. Derivative would be cosine x. And the antiderivative of 1 minus u squared du equals u minus 1/3 u to the 3rd plus c. Plugging sine back in for the u's, we get the answer that you see there at the end. And I only have 10 minutes, so my time is up.